Hey geeky researchers, welcome to another video. So today we are going to see about lasso regression. So we all have heard about linear regression. So where we will have a target variable or our dependent variable, and we will be having some independent variables that will be used to predict or explain the outcome of this particular dependent variable. In agriculture point of view or in plant breeding point of view, this trait could be grain yield. So this linear regression analysis is the most common one that we usually use for our papers and research purpose. But however, this can lead to some overfitting. So overfitting in linear regression is very common because let's take an example from a data set that I have today. So this GYP is the yield. So this is our dependent variable, and there are few independent variables that we are going to use to explain this GYP. But in agriculture data or in many of the practical scenarios, what we have seen is that we have a problem of multicolinearity, which means that these independent variables, say these D50, PH, FLL, FLB, NPT, these traits will be correlated to each other. So these often if you produce a correlogram or a correlation matrix, you can see that these traits will be significantly correlated to each other. So this can lead to overfitting in a simple linear regression. So to overcome this, we have some regularization procedures in regression analysis, and there are two types. One is L1 regularization and L2 regularization, and today we are going to see lasso regression, which is a part of this L1 regression. So let's see how we can do this using RStudio. So to know about lasso, this will perform a variable selection by making the coefficients of the insignificant variables or the insignificant independent variables to 0. Thereby it will eliminate the irrelevant features. So let's see how we can do this using RStudio. So let's open up the RStudio and let's import that dataset. So let's click on import dataset. Let's browse that file. Let's take that. So this is the dataset. Just click the import. So for example purpose, I will be only taking a handful of independent variables to check with our dependent variable. So let's go to our script file. So for this one, you need the library called glmnet, which is a general linear model network package. So if you haven't installed it, just type install.packages and in double quotation just give glmnet and click Ctrl plus enter. It will install, but I have installed it already, so I will just call that library glmnet, and press Ctrl plus enter. So the library is now loaded. So we have our library and our data set. Now we need to specify which is our dependent variable or our target variable, and which are the predictors or the independent variables that we are going to use today in our analysis. So for our dependent variable, let's say y. So y, let's assign y equal to reg $. Let me get the dependent variable, which is our GYP. So that is set, and y is equal to, so once y is given, now let's go for x values or our independent variables. So let's call the function data matrix and reg open a square bracket and specify the columns that you want to do that. Let's see, I'm going to just take a couple of independent variables. So one is plan height, another one is FLL, another one, let's take FLB, let's take NGP, and grain weights. So this essentially takes these columns and converts it to a matrix. So yep, so that's also has been defined. Now we need to define a lasso model using a function called cv.glmnet, so which is a function of this library, which will give you the and this function will perform cross-validated lasso regression to create a plenty of lambda values, and we will be selecting the best lambda value from that lot. So for that, let's define that model. Let's say model, and let's call the function cv.glmnet. You can see it is a function of that library. Just click enter. Let's give our x value and the y value, and alpha is equal to 1. So this alpha equal to 1 is the command to call that to do that L1 regularization on our x and y data. So we have defined that. So from that we need to select the best lambda. So best lambda, let's define that variable, best lambda equal to, from that model. So you can see a whole lot of values available from that model that we have run in our previous command. There's the lambda, CVM, CVST. We'll only need this lambda dot minimum, which means this gives you the minimum mean cross validated error value, and this will be our best lambda value for fitting our original model. So let's select that and click enter. So let's see what's this value. So best lambda, so it is around 0.17, and you can also plot this model. It says here, so this is your mean squared error for this lambda value, and you can see the best lambda values in this range, and we have selected the minimum possible value from this lot. So you can use these plots, and so we have got our major criteria here, which is our best lambda. Now we need to fit the model to see which are the features it is going to reject and which are the important features it is going to retain. So let's fit our best model is to glmnet. Let's run the same formula. Alpha is equal to 1, and now as an extension of the previous command we need to specify that lambda now. So that lambda is equal to best lambda. Yep, so we have run the model. Now we can see the coefficients. What are the coefficients that has been identified by this best model? Once we click enter, you can see I have used 5 parameters, 5 independent variables, and out of that 5 parameters you can see here the results: plan height, FLL, FLB, and GP, GW, and the lasso model has made this grain weight as an it has determined that GW as an irrelevant feature and made it to 0. The most contributing independent variable explaining this GYP dependent variable is FLB, which has 27.04, and remaining are contributing but not as much as that FLB. So you can use all the independent variables that you are interested in and see what is the result. And so by this you can select the variables that you need, but always remember we need to check the validity of this model. So for that we need to calculate R square. For that we don't have a direct method, so we need to calculate few parameters before that, so that we can determine the validity of this current model. So for that we need to extract the predicted y value. So let's say y underscore predicted is equal to, let's use the function predict, and we need to predict that from our best model. Select that, and s equal to, using best lambda, new x equal to, giving the x value. So this will give a predicted a theoretical y value. That's done. Now we need to calculate the total sum of square. Let's say I'm giving it as SST. You can give it as any name, any names that you need. The formula is sum, open double brackets, so y minus mean y, and after this one just square it with 2. So this formula will give you the total sum of square, and we can have the error sum of square, let's say it as SSE, and again the formula is sum, so y underscore predicted minus y square root 2. So we got both total sum of square and error sum of square. Just visualize that value. Yep, it's around 6,535 point something in for total sum of square and 1,471 for the error sum of square. Now from this we can easily calculate the R square value. So R square is equal to 1 minus SSE divided by SST. And let's see that R square value, which is around 0.77. So this means that this model explains 77% of the variations that is shown in our dependent variable, that is GYP, and remaining for around 27% is not explained by these predictors. So you can include more predictors to improve the model. So this is how the thing is done. So as a suggestion I would like to give you guys is that once you have raw data, get a mean values of those predictors and your dependent variable, and run a simple linear regression first, see how that model performs, and before that make sure you run the correlation matrix to see the multicolinearity if it is a problem for you. If it is not a problem for you, a simple linear regression is enough. But if there is plenty of like significant multicolinearity issues, then you try Lasso, and again try another one called ridge regression. Then compare these models and calculate the R square and determine which one works for you the best. Yep, so that's all for today, and in our next video we will be seeing ridge regression. Thank you for listening, and I will provide this code in our website. You can download it from here. See you guys next time. Thank you.